It wasn't until 1974 that someone bothered to ask the question, why do we believe Newtonian gravitation at laboratory distances? And he went through a lot of the historical measurements, and this happens quite a bit in sciences. Someone goes through an old data set and looks at it in a different way, and they find something kind of anomalous. Is it a real effect? Is it just the effect of accumulated errors or stuff like that? And he plotted these distances, but this time is a function of the separation of the test objects in the laboratory. Here you can see these are like 20, 40, 60, 80, 100 centimeters. And then the value of what g would be for that distance. And here's the green line that corresponds to our modern value of g. But here's the line you get if you curve fit these points here, taking into account their error bars. Now there was actually a lot more data sets, and the guy didn't include a lot of them for various reasons. And I probably should go through and check on some of the details of that. But one of the fascinating things about this was, with this line, you will not get closed orbits. In other words, if someone had used the laboratory measurements of g and determined Newton's law of gravity from laboratory measurements, they would not have obtained a law of gravity that leads to orbits. They didn't have enough precision back then. Considering that this is almost 20 years after they orbited the first spacecraft, think about what that would imply if someone didn't believe the astronomical evidence of Newtonian gravity. Well, some of you might remember this because this actual result actually started a little bit of a controversy. Again, I point out that here's the gravitational law that this line implies. They went hunting for a possible fifth force. Back in the late 70s, throughout the 1980s, and maybe even into the early 90s, there was a lot of talk in physics news and stuff like that. They were looking for something called the fifth force, because they thought that maybe gravity was augmented by some other force at laboratory distances. Because they weren't sure, was this effect real or was this just an artifact of their measuring technique? There was a long-running jokes about how hard it was to measure the gravitational constant. In fact, one of the guys that I work with tells a story of he was involved in one of these experiments where they kept getting a perturbation in their results at 3 o'clock every morning. It turned out to be that on the other side of their lab there was a late-night computer operator who had a cot on the other side of the wall, and he would go and sleep on that cot at night and perturb their experiment. Tells you how hard it is to shield against gravity. But these are the kinds of things you had to worry about. We steadily improved our measuring techniques, a lot of abilities to shield out other effects and stuff like that. By the 1990s, we had finally improved the techniques that we confirmed the Newtonian gravitational law, 1 over r squared, down to scales of less than 1 millimeters. There was also interest in this because some fundamental theories, like string theory and higher dimensional theories and stuff like that, imply that there might be some other short-range forces that you could use to diagnose them. So that's part of the thing that was driving that interest. But anyway, any other questions or? Okay. Well, I'll move on to the next topic here. Now, in terms of what Newton started, and well, actually going back to Galileo, the sort of systematic investigation of the world around us, of nature and such, it had a lot of impacts throughout Europe and got a lot of people thinking about things. In 1802, a gentleman named William Wollaston noticed that when he had a prism and passed sunlight through it, he got the rainbow colors, but at one point he began to notice that there were little lines, little dark lines scattered throughout it for the case of sunlight. And it's kind of sad that he didn't think about it a little bit more, because it wasn't until 1815 that Joseph Fraunhofer decided that maybe these lines mean something, and maybe we should, systematize them enough so that when we want to study them, we know what we're talking about. We can say, This is what we're talking about, X, Y, or Z. So he went and he developed a labeling system. Now there's actually an A line way up here, which is actually over in the dark end of this scale in this particular color mapping. But he used uppercase letters for the darkest lines, and then he used lowercase letters for some of the fainter lines. And this notation actually survives to some extent today. Around 1823, William Herschel would suggest that, you know, maybe these lines tell us about something about the composition of the stuff we're looking at, the stuff that's emitting the light. Well, because this is Europe and there's not yet radio communication, news is kind of slow to travel because, you know, some years later, some guy is claiming, well, you know, the nature of stars is never going to be known. But he hasn't been paying attention. About 1860, Robert Bunsen and Gustav Kirchhoff, Bunsen of Bunsen burner fame actually, establishes that all known chemical elements seem to have a unique signature of lines in its spectrum. And they identified many of these in the sun. I've got them marked here for some of these here. These notations, the sodium D line, that's a hydrogen F. Let's see, where's the there's the calcium lines here, H and K, which are actually quite common in other stellar spectra. A lot of these notations survive in astronomy today, and astronomers use them. Well, all of a sudden they had a new tool, and everyone tried to use it. And one of the guys that was really good at this was a fellow named William Huggins, who, with a spectroscope, he started pointing it with a telescope to the planets and fainter objects, including the nebulae. Now, the nebulae were just little fuzzy objects in the sky. Bear in mind, we didn't know what these things were yet. This is still in the 1860s, and there's a lot we don't yet know about these things. He noticed that while the sun was displaying the dark lines against a bright rainbow background, like what we saw before, some of the nebula, not all of them, some of them displayed bright color lines against a dark background. Today we make this distinction as an emission spectrum, where you see the lines against a dark background, versus an absorption spectrum, where it's dark lines against a rainbow, a bright background. Well, around 1864, he pointing this thing at I can't remember which nebula this is, in Draco. I think it has a common name. He finds a bright green line in the planetary nebula in the constellation Draco. He initially thought it was nitrogen, but further analysis by later researchers demonstrated they couldn't identify what element it belonged to. A few years later, Pierre Janssen and Norman Lockyer, while trying to do on an eclipse trip, which incidentally they were trying to find the planet that Leverrier was trying to predict was near the sun due to the perturbation of the planet Mercury. So these stories are all tied together in very weird and wonderful ways. He finds an unidentified line in the solar prominences. Basically, right before the eclipse, they had their spectrometer slit pointed at the sun, and just as the sliver of the sun is occulted by the moon, and there's just a sliver there, it acts like the slit in a spectrograph, and it gives you this curved spectrum here. If you look closely, you'll see there's little prominences and stuff like that, and it gets you what they call a flash spectrum. I believe the line they're talking about in here, he suggests that as a result of this other unidentified line, they suggest that, well, maybe it's some unknown, undiscovered element, and they decide to call it helium for Helios, the Greek for the sun. Around 1870, Dmitri Mendeleev publishes a periodic table which becomes the precursor of the one we use today. The big difference between Mendeleev's table and other tables is Mendeleev used the behavior of the elements, the chemical properties, how they would bind to other elements to determine where they belonged in the periodic table.